Hi, hi y'all. Second video drop. Today, we want to be able to get you to start doing basic normal curve problems using the rule of thumb that's known as the 68, 95, 99.7 rule. We'll also want to be able to understand what the standard normal curve is. So let's go ahead and get started. To draw out the standard normal curve, there's a couple things I'm going to be asking you to do on almost every problem. At least I would ask you to do it in person. We're going to draw a horizontal axis. We're going to draw a bell-shaped curve. Because you, me, and Dupree all struggle at drawing very well, what I require almost every time is to put an end notation up there in the right-hand corner that stands for normal curve. And then you're going to put well, right now, since it's a standard normal curve, I'm going to put 0 and 1. But what this 0 means is it's the population mean, and this 1 means the population's standard deviation. Now, our standard normal curve is this. We put the mean right in the middle of the hump, and it is 0. When we have standardized everything, taken everything down to z-scores, then our mean is known as 0. Also on the standard normal curve, there are 3 standard deviations above the mean. So you imagine positive 1, 2, and 3. And then there are 3 standard deviations below the mean. Negative 1, negative 2, negative 3. And this represents our standard normal curve. Sometimes you'll see people write things like this using the standard deviation notation. Either way, that's going to be the standard normal curve that we try to work on throughout the problems today. Go ahead and erase. Okay, so what we have found, just to draw this off to the side before we start on number 1, is in terms of the 68, 95, 99.7 rule. What we have found on any normal curve, a great rule of thumb to redraw some of this. Is that between 1 standard deviation above and below, the amount of data under the curve, and this is the amount of area under the curve, something like that for those who use stats students, but this area right here is consistently really, really close to 68% of all the data. And you'll see some different problems. We'll answer some problems here in number 1 that can get us there. If you see where this is going, then you'll know that from 2 standard deviations above to 2 standard deviations below, this would then have 95% of the entire population under this normal curve conditions. And then finally, from 3 standard deviations below to 3 standard deviations above, this has 99.7% of all the data possible. What I'm then going to do is keep that in mind as we go about this problem. So up here in the corner, I'm going to draw a normal curve relative to the context. So a normal, let's see if I can fit all this in, 30,000 with a standard deviation of 2,000. I apologize for running off the screen here. What that allows us to do is put a 30,000 here. Allows us to put a 32,000 because 1 standard deviation above, 34,000, and 36,000. Then 28,000 because 1 standard deviation below, 26,000, 2 standard deviations below, 24,000, 3 standard deviations below. When it asks us 68%, what we do is we go down here and we say, oh, 68%, you're asking for the difference between 1 standard deviation below and 1 standard deviation above. And we see that right here and right here. So we're going, this is 28,000 kilometers and 32,000 kilometers. Then the next question refers to the 95%. So now we know that we're 2 standard deviations above to 2 standard deviations below. So we look here, and we're at 26,000 to 34,000. We're giving ourselves a little bit of leeway because we want to capture more of the population. What percent of tires will have a life that exceeds 26,000? So this is why we draw out our normal curve in the first place. When we say 26,000, what we're going to do is go draw our line right here at 26,000. To exceed would be on this side. Now, if we're looking down here at our 68, 95, 99.7 rule, we notice that there's nothing that represents that, but there is a way that we can tie in there, right? If we know that 95 comes to right here, then what we can reasonably say is with 100% of the data and subtract out that 95%, there's 5% left not accounted for here and accounted for here. So if we divide that up, the two regions that are mirroring each other, we're down to 2.5%. So what we know is right here is 2.5%, and right here is 2.5%. And what that allows us to do is, if you notice, that correlates to up here, 2.5%. So to answer C, we go 1 minus 2.5%, and we get 97.5%. If a company purchases 2,000 tires, how many tires would you expect to last more than 28,000 kilometers? Well, I'm going to have to write over some issues here, but 28,000 starts right here and it says more than. So we shade our desired thing. Again, let's pay attention to the red this time on the shading. Now we're going to use a lot of the same logic that we just used. We'll notice that 28,000 is -1 standard deviation. So we come down here to -1 standard deviation. We look at that we're in the 68% region, right? So if we do 100% minus 68% to get out that middle region, oh, what is that, 32%? From there, what we know is this region entirely and this region entirely combined to make 32%. So if we divide it by 2, I think we get 16%, which implies that this right here is 16%, which means the area here that we need to subtract from 1 is 16%. So to answer this last question, part D, what we'll do is 100% of the curve minus out the 16% that is not accounted for, not shaded in, and get 84%. From there, we're going to do an expected value problem, which we would have established in chapter 5. And if we want to figure out of the 2,000 tires, we think that 84% of these will be able to last more than 28,000 miles. So I'm going to go 2,000 times 0.84 and get 1,680. And that's a good introduction problem. Let's hope we don't bore you the rest of the way going after the rest of these. Shelf life of a particular dairy product is normally distributed. Draw my normal curve. 12 days mean, 3 days standard deviation. So I want to start mapping it out. 12 days mean right there. 3 above, 3 below. So 15, 18, 21, 9, 6, 3. This is my playing field for this particular problem. About what percent of products last between 9 and 15 days? 9 and 15 days. Well, if we do recognize what would that's one standard deviation below and one standard deviation above, then we can sit there and say that this is 68%. What percent? I wonder how good I can be. Ooh, impressed by my talents? You should be. Okay, what percent of the products last between 12 days and 15 days? So now we're looking at something where we want to find this. Here's the way I think about it. There's the mean, and we know that one standard deviation below and one standard deviation above. This is 68%, right? Well, if you look over there at the area, what I've done is cut that area in half. So what I can do is go 68 divided by 2 and get 34%. So this is 34%. See how talented I am with the eraser again. Oh, not as talented that time. Okay, what about what percent last 6 days or less? So there's where we're going, 6 days or less. I like to shade it in to translate this so I know what my goal is. It looks like my reference point is going to be 2 standard deviations below the mean. So 1, 2, plus 1, plus 2, minus 1, minus 2, because that tells us that are 95% between, which means out here splits the remaining 5%, which means this has to be 2.5%. And finally, about what percent of products last 15 days or more? Can I get in there? Ooh. 15 days or more. Okay, here's what I'm going to do. I'm going to pull on a previous problem. When we think of mu, 1, 2, 3, 1, 2, 3, -1, -2, -3. So right at mu, there was 50% to the left and to the right. What we then know from problem B is that this was an additional 34%. So we've used up 50 plus 34, we've used up 84%, meaning the shading that we got left right over here has to be 1 minus 84, which is 16%. And this is how we're just going to basically torture this 68, 95, 99.7 rule over and over and over and over. Let's see if we come across anything more. I think we can answer this one. Let's start to draw out a situation. I got to be very careful about the problems I choose in terms of where the standard deviation falls. Otherwise, we're not quite ready to make that calculation yet. But either way, we got a normal, we got a mean of 20 minutes, we got a standard deviation of 4. So if I put that mean 20, 1, 2, 3, 24, 28, 32, and then 1, 2, 3, 16, 12, 8. What percentage of people 28? See, we're really lucky that this 28 falls right on a standard deviation for more than 28 minutes. So more than 28 minutes. Let's see if we can start to parse our way there. Standard normal curve, 0. -1, -2, -3. Outside of 2 standard deviations, this was 95%, which previous calculations then told us that this was 2.5%, which meant this had to be 2.5%. which matches our area that we're going for. So this had to be 2.5%. If 2,000 ticket buyers were in line, how many of them would expect to wait for less than 16 minutes? So now let's ignore this and let's go less than 16 minutes. Less than 16. Less than 16. That is one standard deviation. So see if I can erase and try to reborrow some of this. Oh, come on, eraser. There we go. Less than 16 would be one standard deviation below. So we're going one standard deviation below, which means if we can pull on some past ideas, here's 50% above the mean. And if you remember, between 1 and 1 here is 68, which means half of this has to be 34. So what I'm doing is 50 plus 34 is 84. Subtracting that out. Whoops, what am I doing? Going 1 minus 84 is 16, which must mean that for this less than 16 minutes is 16%. Now, because it's an expected value problem, we're going to go 2,000 times the 16% and get we'd expect 320 ticket buyers to wait in line for less than 16 minutes. Plowing on. If you remember way back in the beginning of the semester, we talked about percentiles as the percent of data that falls below a certain person. So when Mike got an 85, what we need to have happen is this 85 to end up right on a standard deviation mark, which we'll see. So 75 mean, 5 standard deviation. Let's draw this out. 3 above, 3 below. I wish I was a better drawer for you, but I'm not. Okay, so Mike is supposed to be an 85, right? So Mike is right here, right on. There's mu, there's +1 standard deviation, there's +2 standard deviation. So he's 2 standard deviations above the mean. When it says what percentile does he fall in, we're wondering what is the percentage of people below old Mike here. Let's pull on that idea that if we go mu 1, 2, 3, 1, 2, 3, that we know that 2 standard deviations below, 2 standard deviations above is 95%. 100% minus 95% is 0.05 or 5%. Divide that by 2 because there's 2 areas unaccounted for, and we get 2.5%. So the reason that matters is this area right here is 2.5%, which means the shaded area is 1 minus 2.5%, which puts Mike at 97.5. So Mike is in, we go to whole percentiles and we want percent below. So Mike is in the 97th percentile. Plowing on. In an Oreo factor, the mean mass of cookie is given as 40 grams. For quality control, the standard deviation is 2 grams. If 10,000 cookies were produced, how many cookies are within 2 grams of the mean? Interesting. This is going to be a pretty quick one, I think. Normal. Boy, my drawings are getting worse the longer this video goes. 2. So we go mean 40. 1, 2, 3. 42, 44, 46. 38, 36, 34. Within 2 grams of the mean would be there to there. And I think that's right on the button, our 68%. No, because of 10,000 cookies, we're going to have to take 10,000 times 0.68 and get, what, 6,800? Let's use my calculator there. Cookies are rejected if they weigh more than 44 grams. More than 44 grams. Or less than 36 grams. The great thing about this problem is in terms of solving it, this is -2 standard deviations and this is +2 standard deviations. So we know the acceptable range in between here is 95%. So if we do 1 minus 95%, where we're at is a 5% rejection rate. So if we take 10,000 cookies times 5%, we're going to get 500 rejected cookies. Sad face. Bye, Oreos. I'll never reject you. Oh, I think this might be the last problem. Don't hold me to it. If you're powering on and sticking with me this long, I'm really proud of you. Let's get after it. The speed of cars on the highway have a mean of 95 and a standard deviation of 5. Let's map out our playing surface here. 1, 2, 3. So 100, 105, 110. We go 3 standard deviations below. We're at 90, 85, and 80. What percentage travel less than 85? Less than 85. Here's what I see. I see this was our mean, right? So this must be 2 standard deviations below. Imagining mean 2 standard deviations above, 2 standard deviations below. Our rule of thumb says this is 95% of the area, which divide by 2, 2.5%, 2.5%. We've done that more than a couple times. So what percent? This equates with this. 2.5%. Some of that out of the way. Some of this out of the way. If a police car stops cars going more than 105 kilometers per hour, how many cars would stop if there were 8,000 cars on the highway? This is why I should keep what I'm doing. 95, 5, 95, 1, 2, 3, 3, 100, 105, 110, 90, 85, 80, more than 105, more than 105. If I take this thing, I notice there's mu. That's 2 standard deviations above. I think we just did this problem right here. Outside of 2 standard deviations to the right of it is 2.5%. If we take 8,000 cars times 0.025, we will get, we'll expect to pull over 200 cars. Am I out? Whew, brutal. One more problem. The mean life of a battery is 50 hours with a standard deviation of 6 hours. Not 50, silly. The manufacturer advertises over price to all batteries that last less than 38 hours. There's mean, there's -2 standard deviations. I think we've done this one multiple times, but just to show you again, if we go 2 standard deviations above, 2 standard deviations below, in a standard normal world, What we know is this is 95%, which means outside of here has to account for the extra 5%. 1 minus 95 is 5%, because we got to split that amongst two places, means 2.5%. So this problem here, 2.5%. All right, looks like I just clicked through because I was getting a little impatient. Looks like we're going to take 2 more questions to take it home. Brutally long video. A grading scale is set up for 1,000 students' test scores. It assumes that scores are normally distributed with a mean of 75 and a standard deviation of 15. How many students have scored between 45 and 75? Now, there's a good problem that we haven't done yet. So 1, 2, 3, 1, 2, 3. I'm just going to leave this one for A. So 80, 90, 105, 120, 70, 60, 50, 45, 40, 30. Between 45 and 75. In a standard normal world, here's the mean. We're 2 standard deviations below. So we're pulling on the idea that this is 95% of all data, but the mean should always split everything perfectly in half, which is what's happening here. We're between the mean and 2 standard deviations. So if we just divide this by 2, I think it's 47.5. We get 47.5%. So 47.5%. If 60 is the lowest passing score, how many students are expected to pass? Try to map out our problem here a little bit. Let's go to part B. Normal 75, 15. Mean of 75. 1, 2, 3, 90, 105, 20, 2, 3, 30, 45, 60. So we want to pass. So 60 is our dividing line, and we're worried about 60 and above. Here's what I'm going to do, guys. I know from here over is 50%, the mean, right? This is 1 standard deviation below to 1 standard deviation above was always 68. So if we take 68 and divide it by 2, then this has to be 34%. So if how many are expected to pass, we go 34% plus 50%, and we get 84% total. One final problem. Thanks for your stamina. The monthly income of 5,000 workers at a Microsoft plant are normally distributed. Suppose the mean is 12,500. Standard deviation is 2,500. Here's what I'm going to do, guys. I'm not going to draw this out perfect or explain all my work perfect. I'll explain some of it. Hopefully by now you're following along. So maybe you can do it ahead of me, press pause on your play button, and then just check me for answers. What percentage earn more than 1,500? More than 1,500. Let's see, 50%. I'm going to do 1 minus 50% minus an additional 34% and get 16% for that one. What percent earn less than $750 per month? Let's see. I'm going to do 1 minus 50% minus an additional 47.5% and get 2.5%. What percentage of workers earn between 750 and 1500? Boy, that's an interesting one right there. So between one standard or two standard deviations and the mean is 47.5%. Taking 95 divided by 2, and then between the mean and one standard deviation is another 34%, taking 68 divided by 2. So 47.5 plus 34 equals 81.5%. What percentage of workers earn less than $1,750 per month? Here's what I'm going to do, guys. This is plus 2 standard deviations above. We figured out a million times already that this is 2.5% here. So if we're going less than, which is all of this, I'm going to go 1 minus 2.5% and get 97.5%. You're a real OG if you actually made it this far. I hope you learned it long before question 9. There will be a quiz that follows on the Google Classroom. Have a great day.